Hello and welcome to 12th lecture in 19th chapter of our comprehensive course on AI, ML and DS. Now we wanted to talk about these three continuous distributions and these three discrete distributions here. Later on we will take few more also, but here at present these three and these three. So first, uniform distribution. Okay. Now uniform distribution, as the name indicates, here this is a function which is ranging from A to B. Okay. This initial portion just ignore, but the function ranges from A to B. That means here it gets the value this much where it starts, and throughout the range the value remains constant. So the name itself is clear, uniform distribution. Throughout the range the probability remains constant, and therefore cumulative probability, if you want to find at any x value, then you can find it very easily using these equations. Okay, for example, if I take x is equal to say mu only, so if x is equal to mu, then x is equal to a by 2 minus plus b by 2. So a by 2 plus b by 2, that is x, right, minus a. So b by 2 will remain, and a by 2 minus a, that will be minus b by 2. Think. So that means this in the numerator will be b by 2 minus a by 2, or b minus a whole divided by 2, right? So b minus a whole divided by 2, and this is b minus a, so b minus a will be cancelled and 1 by 2 will remain. So that means if x is equal to mean, exactly mean, and where will be the mean? This is a uniform distribution. So if this is 5 and this is say 15, then 5 plus 15 divided by 2, that will be 10. Exactly at the midpoint there will be mean. Then what is the cumulative probability of any big x having less than mu? Because I am saying x small x is equal to mu, that is the value which I am taking for simplicity. Okay, so that answer we got, that if x is equal to mu, then in that case this is a mu minus a, or that is a plus b by 2 minus a, or that would be b minus a whole divided by 2, right? And that would be b minus a would be cancelled, so 1 by 2. So if this is exactly midpoint, then how many data points, or what proportion of data points would have value less than x is equal to mu, or midpoint? So obviously 50%, because the distribution is clearly showing that 50% of the data points are having value less than this mu. Okay, so uniform function is very easy, and for uniform function the mu is given by simple arithmetic mean, and sigma standard deviation is given by b minus a whole square divided by 12. Well, this gives the cumulative probability of any of values x less than small x. Okay, I showed for one specific example. When you put small x is equal to mu, then you get cumulative probability is 1 by 2, because small x is equal to mu point comes here, and half of the triangle will be shaded and half will be unshaded, right? Now where is this used, uniform distribution? Then it is used for random parameter initialization in neural networks. Now these neural networks are one of the hottest topics in data science currently, because all the most sophisticated research level work is either being done in deep learning, or which requires neural network again, or it is done in computer visions, which also require neural network, or it is being done in NLP. The best example of this is that our favorite nowadays chatbot, that is the ChatGPT or any other chatbot like Llama. So this also require neural networks. Of course, in chatbots there is something called encoder and decoder stacks also, but that is okay. But basic logic is you have to understand neural networks if you want to understand its working internally. Now a neural network is inspired by human brain, and these are suppose the cells of the human brain. Okay, and we say that just like human cells, or that is neurons, they are connected with each other using dendrites. Similarly, these neurons, artificially created neurons, which are actually called perceptrons. So these perceptrons are connected with each other using connections, and when you give some input from this side, from the left side, then when that input moves to from first neuron to here, it gets modified by some weight parameter. So here this line has suppose weight 2, then if I give input 5, then this will get input 5 multiplied by 2. So because 2 is the weight of this line, but the second line has suppose weight 1. So if I get input 5, then this will get input 5 only, like that. So each, though inputs are same, and from same input I am taking to these also, these also, these also, these also, various other second layer neurons, but the edges have different weights, and therefore this each different neuron of the second layer will get a different input. Then same process continues here, same process. So these are called edges in the neural network. Now what are the weights, and how to initialize these weights? Initialize the weight means whole neural network works like this, that it automatically tries different values of weight until the loss is minimized or accuracy is maximized. And for that, wherever the loss is minimized or accuracy is maximized, that value of the hyperparameters, that will give the best possible neural network model. Okay, so what is hyperparameters, that we have done earlier just now in 3-4 lectures back with the permutations and combinations. So if you don't remember, then you please see that. Okay, so depending upon what weight you start with. So suppose initially I start with here weight 2, here weight 3, here weight 1, here weight 0.5, here weight 1.5, like that. Okay. Or someone starts that no, I want to start from here 2 and here 1.5, or here different and maybe 3.5 and 4.5. Just randomly I'm speaking the numbers. So that when you want to start your neural network, and then the neural network starts trying different ways when it iterates through the various layers, and finally you get the output when the neural network converges. That is, it finds the most optimal model for which the error is minimized. Then at that moment you get the output of whatever task you are doing. Either you are doing regression, that is predicting a continuous variable, or you are doing classification, that is the predicting a class, whether the iris flower will have setos or virginica or versicolor. Okay. Or predicting a continuous variable means you are predicting the salary based on, say, age and seniority of your employees. So there are two things. Whatever you are doing, for that you have to first start your neural network with certain initial weights. Now the initial weights what are to be taken, then the standard practice in neural networks is that take a uniform sample, say minus a to a. So that means here weight is minus 2, then here weight would be plus 2, here minus 1.5, then here plus 1.5, here minus 1, then here plus 1, here minus 0.5, then here plus 0.5, like that. So that means they start with a uniform range, or there will be equal probability of each weight being applied on the next layer initially. Thereafter, obviously, the weights will go on changing automatically so as to minimize the error of this whole structure, that is a neural network. But initially, we don't want to bias our neural network by giving more weight to one particular age and one side and less weight to another side. So we take a range minus a to plus a. We know that minus and plus sign don't matter. What matters is the magnitude. So magnitude wise, we give us equal weight on both sides. So as a result, we start in this manner. So most important use of uniform distribution is this. So that means the graph would be minus a to plus a, and a horizontal graph like this. So this small a and b are there. Instead of that, here it will be minus a and here will be plus a, and the graph would be a straight line between minus a to plus a. A uniform distribution we start, so that initially equal probability for each initial value is ensured. Okay, don't worry at all about if you find this whole thing very complicated, but just remember that continuous distribution is used while initializing neural network, because we will do a detailed discussion about neural networks. So at that time I will explain what is each thing. Okay, now this exponential distribution. The exponential distribution is given by this manner, this way. So it shows that as x increases, y exponentially decreases in this case. However, it could be this way also, the mirror image of the upper distribution. So that means as x increases, y also could be increasing also. That is also possible. That is also exponential. But this is called means as one variable increases, other also increases. Okay, while here as one variable increases, other decreases here, while here as one variable increases, other also increases. So both things are possible. That is not the case. But the change is not linear like this. It does not decrease on a straight line path, but it decreases this way. Okay. Now here if I put that how much is the probability of having what is the cumulative probability for small x is equal to 1 upon mu. For simplicity, I take that many. Okay. So small x is equal to 1 upon mu. So if I take 1 upon mu here, then minus mu, that means small x is equal to, not 1 upon mu, I'm sorry, small x is equal to mu, or that means small x is equal to 1 upon gamma. Just like here we do, the probability small x is equal to mu, and we found that 50% of the cumulative probability is there because it is a uniform function. Now same thing I want to find, here this small x I want to put equal to mu, but mu is 1 upon lambda for this, 1 upon gamma for this particular distribution. Okay, so in that case gamma and 1 upon gamma will cancel, so what will remain? 1 minus e raised to minus 1. Now what is that? If I see, it is 1 minus e to the power I am writing this way, and minus 1. Okay, or that is equal to 1 minus 1 divided by e. Okay, or that is equal to 1 minus this 1 divided by e, it has value 0.368 at present, just accept that. Okay, so that means this answer would be 0.632, 1 minus 0.368, so that will be this much, or 63.2%. Okay, so that 63.2%, that is called cumulative probability of x having value less than the mean. Now try to understand, because here 50% was the probability, it was a uniform graph, but here the graph sharply decreases. So if x is equal to mu comes somewhere here, then obviously majority of the probability is already covered in this region, because the area slowly goes on becoming smaller and smaller. So if x is equal to mu is here, or say here only, this is itself, suppose x is equal to mu, that is equal to 1 upon gamma. Okay, so in that case 63.2% is the cumulative probability of this region, and 38.2%, 36.8%, that is the cumulative probability of this region, right? Now what is this e Those who know science background or something, they already know, but E is the base of natural logarithm. Okay, or that means E is the 2.718. That is its value. So this 1 upon A, E, that is this, is 1 divided by 2.718, and therefore that value will become 0.368. That you can check when you are free from this lecture. So I am putting this as your note. So a markdown cell I am putting so that it remains with you. Okay. Now, what is the common example of this exponential process? Then it is the time between events occurring in Poisson process that varies exponentially. Now, what is the meaning that Poisson process is later on going to come in this discrete data, not here, but it is one discrete data distribution. It is the other green colored graph which we had. Mm, this one. Okay, it will come later on, Poisson distribution in today's, next lecture only perhaps. But Poisson distribution is like this. But you can see this is a discrete distribution. But if someone says how its peak value changes, then its peak value changes as my cursor is moving this way. Or here, if I start my graph from this point, because that is just a matter of choosing axis. I can choose my y-axis here, then it would look like this graph. So how my peak value changes, then it would change this way. But can you see that it is the same type of graph? Okay, so the change in the peak values that of Poisson distribution that follows exponential distribution. Here it is written time between events. So this is when we see the Poisson distribution, you will see that this is one event, this is another event, this is another event, this is another event. So time between first and second event, that changes like this. But time between second and third event, that changes this way. Then time between third and fourth event, that is this way. And time between fourth and fifth event, this way. So if I pass through these all, then that would be an exponential distribution. Okay. For example, this is a data science example, that if you take clickstream data, what is clickstream data? I'm talking about it because it is really very interesting. Then the time between consecutive user clicks on a web page can follow an exponential distribution which models the time until the next event occurs. What is the meaning? Suppose you just logged in to Amazon or Flipkart website. While you became member, you already accepted that terms or conditions and privacy policy. Okay. Now, in that terms and condition and privacy policy, you will be surprised that they track everything. Everything means what? They track where on the screen do you click. First thing. Second, in which order do you click? So suppose here these are items on the Amazon website. So first is suppose say display of PC. A screen is there. Second is suppose say some keyboard is there. Third is suppose a laptop is there. Now suppose and fourth is suppose this desktop entire set is there. Now if you click on directly on the laptop and the desktop, so they track that clicking and they decide that this fellow is not interested in buying accessories like screen or keyboard, but this fellow is interested in buying the whole set. So immediately the recommendations will start changing, and you will start seeing the whole desktop or whole laptop depending upon where you have clicked. So first, where you click. Second, how fast your mouse moves. Based on that, you will be surprised. But banks, etc., they track your age, and even these online shopping portals also, they can have an estimate of your age. Okay, and then the recommendation system will recommend items based on that age group. Then, for how long, that is the duration, you stay at one item. So if you just casually browse desktop, laptop, then maybe gaming laptop, then maybe immediately you go to the next item, say football, then suddenly you go to the next item, say clothing brand and all that, then that recommendation engine understand that this person maybe is just doing window shopping. He is not interested in any real shopping. So maybe discounted offer should not be shown to that person, right? But if you spend a lot of time first on this desktop, then all possible desktops, whichever are shown in alternative, HP and Dell and these, then similarly you click on laptop and all possible laptops, HP, Dell, Lenovo, all are shown to you, and you click on each of them, you spend a lot of time to study various features, and then you do the next click. All these things are tracked, or your entire browsing session is tracked, and it is permanently stored in your user profile. Okay, so that is the reason why most of these sites don't allow you to do anything without logging in. Okay, so when you log in, then obviously they have the idea that this is this user, and your entire profile will be saved in the database for your end user ID. Okay, so that is called clickstream data, and on the basis of clickstream data, so many things can be done. So recommendation engines can be made and many other things can be done. Okay, so how you click, say I am clicking this way fast, or I am clicking slowly and examining each item, then this examining each item maybe for 2 minutes, here examining each item for maybe 2 minutes. How many times I change my this window, the go to next window. That is also often used to decide if the user interface is appealing or not. Okay, so all this data, what duration you spend, how many clicks you make, total how much time you spend on your portal, then how much time you spend on each item, how fast your mouse moves, all these things. These are called click stream data, and that click stream data exponential follows exponential distribution, where the user clicks on a web page, then consecutive user clicks on a web page, they usually follow exponential distribution. So that means first click and second click, there the duration is high. Second and third click, then the duration is okay, slightly less, because the person has just logged in, so he will first try to make a sense of the page, what is presented to him. So initially he will not just go on clicking, right? But as he gets used to, within just maybe 2 minutes, he finds that yes, okay, on this corner of page this is there, on this corner of page this is shown, and these are the items in which I am interested, and these are the items in which I am not interested. So then this duration between first click and this is, suppose I am now calling first, the duration between this click and the next click and the next click, that will keep go on decreasing very quickly. Okay, so duration between consecutive clicks reduces exponentially like this. It follows exponential distribution, and based on which several recommendation systems and many other models they are made. Okay, now next is the normal distribution. Normal distribution is one of the most common distribution that we encounter in our daily life. Here I have taken some example also, these two links also. What are daily life examples of normal distribution? But first, let us quickly do what is normal distribution. As I said, the speciality of normal distribution is that here we don't calculate probability by some equation like this, but instead we use Z chart. What is Z chart? If I show you, then it is a chart like a log table, somewhat similar to log table. In your earlier standards, you have applied log table. So this kind of charts are there. This chart, if I make it maximize, then this kind of chart, they are called Z chart. Okay, so then the cumulative probability, when you want to find, there is no equation for that here, but first you find the Z score, and of the starting point. Suppose I want to find cumulative probability between the beginning and this point, so I will find the Z score here. That would be this 0 minus mu divided by sigma, and here I will find, suppose x is equal to mu only, that is the mean only, so mu minus mu divided by sigma, so this will be 0. So that the difference between the two Z scores that I find, okay, and Z score 0, for that you can find the probability, cumulative probability easily, that this much using this chart. Okay, you can see that for every value of Z, positive value, zero value, or negative value, the cumulative probabilities are shown on this axis. So you can easily find that probability, and we will learn to use this Z table, because without this Z table, it is not possible to talk about normal distribution. And normal distribution is one of the most important distribution seen in nature. Some very nice examples. Suppose you have a big container in which the popcorns are being made, and now you want to distribute that popcorns to 5 kids. Each kid is standing in front of you, taking a bowl, and you just drop the popcorns like this from the container. Then the popcorn will get this kind of distribution. That is normal distribution. Okay, then suppose you take a sieve and you throw sand in this manner from this side. This is actual picture taken from a British sieve company which I found from some website. Okay, and if you throw the sand, then the sand mound will be created like this. Okay, again it is a normal distribution. Now you know why most of the mountains have this kind of shape. So nature seems to be preferring normal distribution. Let us take this particular website. I earlier said that two websites are my favorite for statistics. One is Scriber and another is this, that is Statology. Particularly this one because it is free. That one is for profit, so you have to become member. Now 6 real life examples of normal distributions. Okay, so first, what are the characteristics of normal distributions? It is a bell shape, it is a symmetrical. So if this is the mean value, then on either side of mean value you will find equal number of probability distribution. Okay, then unimodal, it has only one peak. A pure normal distribution has only one peak. Mean and median are equal, and both are located at the center of the distribution. So the distribution ranges from -3 to +3. So the mean is -3 plus +3, that is 0 divided by the number of observations, but that would be 0 only. Okay, 68% of the data, this we have seen the 68, 95, 99.7 empirical rule. So 68% of the data falls in 1 standard deviation, 95% fall in 2 standard deviation, and 99.7 fall in 3 standard deviation. Right? Now these are some practical examples. If you take a large sample of babies, newborn babies, and find their birth weight, say you take at least maybe 1,000 newborn babies record, and it is very easy to get that record from municipal corporations, then the birth weight follow this kind of normal distribution. Then heights of males. Okay, so it is seen that if you gather maybe around more than just 200 or 100 males, then their heights vary this way. Some are extremely short, some are extremely tall. This is height in inches. Okay, so this here 61 inch means short, 79 inch means very tall, but there will be very few number of, and this is the count outer frequency. So there will be very few people who will have this much short height, and similarly very few people who have 79 inches. 79 inches means 6 feet and 7 inches, that much height. Okay, but majority of the people will have moderate height, 69 inches. 69 inches means 5 feet 9 inches. Okay, so majority, largest 140 count is seen for 5 feet 9 inches, right? Here also the chances of being so underweight, so that it is maybe 6.7 pound at the time of birth, is very less. Count is hardly 10, and the chances of being so overweight, 8.5 pound at the time of birth, that is also very less, around 20, but around 10. But chances of having average weight, say 7.4, 7.5, and 7.6, then the counts for that is the highest. You can see 120 or 140. That is the count for these three middle tall bars in the this histogram like chart, right? Okay, shoe sizes. Now, if height varies according to this, then obviously the shoe sizes for male will also vary according to this. Now you know that. See, what happened is, when the online shopping portals came, then certain professions thought that their business is safe, because, for example, the shoe shops, they thought that how can one buy shoe online, because say uh, for that one has to actually go to shop and measure, get his foot measured, and try the shoe. But actually, shoe or the height, and that means the for height is mattering for clothing. Okay, so tailors also thought that their profession is safe. Shoe shops also thought that their profession is safe from the online onslaught. But these firms nowadays very easily, even this sell shoes online or clothes online, a t-shirt or a shirt or a pant online, because you will be surprised, but there are hardly a few varieties in our height and build, and similarly there are hardly a few varieties in our shoe sizes. Okay, and the distribution is also known. So shoe companies who produce the shoe, they also follow this way only, that they will produce maximum number of shoes in this size, because they these sizes are in highest demand. Okay, so this bar, this bar, this bar, this, and this bar. Okay, their count of people having that size is more. While if you have extremely small foot or extremely large feet, in that both cases you find it difficult to get shoe. Not only shoe, you find it difficult to get clothing also, if you are very short or very tall, right? So these things is actually already sorted out, and once you buy one item from online portal, that their height you have, they say you bought one ready-made shirt from there, and you did not return it, because they offer 15 days free return window. You did not return it, and you even give the rating also 5 star. So they know that this your profile is created, that this person wears the shirt of this many, say 42 inches. So obviously, if his shirt is 42 inches, then his shoe will be this much. That's it. The matter is over. Okay. So no profession or no item is safe from the onslaught of online retailing. Okay. These are ACT scores, ACT or SAT or any competitive exam scores that follows this kind of distribution, and this is used as a diagnostic. If suppose some allegation occurs, for example, here recently in India, in the NEET, that is the medical entrance exam, some allegation occurred that a paper was leaked, and it was proved that the paper was leaked. Then the question is that what was the magnitude of that leak? So that means that say police arrested those 2-3 agents who leaked the paper, and those around 20-30 students who benefited from the leaked papers. But the question is, was the magnitude of the leak confined to only those 30 students? These 30 students paid lakhs of rupees. So maybe it is possible that the agents gave paper only to them. But what if the paper through social media or something spread all over India? So if the leak spread all over country, and if majority of total 10 lakh people appeared for the exam, and suppose the leaked paper reached 8 lakh people, then the data distribution will not be like this. It will be very distorted, maybe like this. So many of the people will have high marks or something, sorry, high score is on that side. Okay, so it would be like this. Okay, so many of the people will have high score, and very few people will have low score. But if there was no large scale leak, then the data distribution would be normal. And it was found in the NEET case that as a whole, whatever scores the whole population of 10 lakh students got, that had more or less normal distribution. So it was decided to the Supreme Court of India decided that okay, leak occurred, and these culprit students and the agents, they will be barred, and they will not be allowed admission, but we will not cancel the entire exam for that. Okay, because think about the hardship to 10 lakh students if their exam is to be taken again, and no guarantee second time it will not leak. So you have to decide, if leak occurs, then you have to decide what is the magnitude of leak, and that can be decided by this distribution of scores. So if high scores are too many, then the graph would be like this. It will not be a symmetric bell curve, but it will be highly skewed graph. Okay, so then you will say that it is leak. Another example of normal distribution is average retirement age of NFL player in any sport, it is seen that some players are excellent fitness, so they can play up to 43 years of age. Some are very poor fitness, so they have to retire maybe due to injury, unfortunately, at 25, 26, 27 years of age. But majority of the players are normal. They are not excessively good athletes, but they are not poor also, and injuries occur rarely. So that is why majority of the count is on this 3-4 bars. Okay, so majority of the players have this retirement age of 33 years because sports are highly demanding. So 33 years is considered old age. So around 31, 32, 33, and 34, that much, or 35 maybe, in that region, majority of the retirement age will fall. Then blood pressure. Now blood pressure, then say diastolic blood pressure in human beings, then it was found that it is around 80, but there is this standard deviation of 20. Okay, that one must understand. So if your blood pressure comes out to be 70, of course you should consult the doctor, but if doctor says that there is nothing to worry, then you should not run from one doctor to another, because 80 plus or minus 20, one standard deviation. So you can say 70 is well within one standard deviation, so fine. But 80 has the maximum count, 78 has this much count, 70 is slightly abnormal, but not extremely rare that you can see. And similarly, 90 is also slightly abnormal, but still it is not very rare. More than 60 count is seen in your total sample, which who have 90 blood pressure. But 98, that is extremely high. That is the case of hypertension. And 64, that is also extremely low. Okay, so this type of people are always marked. Okay, this technology is a really interesting side. Just like these were the examples of normal distribution, you can see there are links. Example of Poisson, example of binomial, example of geometric, and example of uniform. Okay, so we will do them. Uniform distribution, I think we have already done. So one neural network example I said, but guessing a birthday. So if you guess the birthday of person, walk up to a random person and just guess that your birthday would fall on this date. That then you find second person and your birthday would fall on this same date, or maybe some other date like that. Then third person, and so on. You take a sample of say 10,000 persons and you just guess that your birthday falls on this date, and then you plot a graph and check it. If you are correct, then you take that as a assumption, true assumption, or false, then also you take it as a wrong assumption. But now your probability of being born on every day of the year is same for human beings. It is not that human beings prefer. Now I'm not talking about that planned pregnancies in which people plan that my child should be born on New Year only or something. But if there are no interventions like that, artificial interventions are not done, then the chances of being born on every day are equal. Okay. So probability of being born on January 1st, 1 upon 365. January 2nd, 1 upon 365. 1 upon 365. So as a result, if on this axis there is date and on this axis, y-axis, there is probability, then on every date the probability is equal. So it is a uniform distribution, right? Then rolling a die, that is also example of uniform distribution. That probability of getting 1 is 1 by 6, 2 is 1 by 6, 3 is also 1 by 6, and so on. So here, if say, there are some say these trials, first trial, second trial, up to sixth trial of rolling the die, then the probability throughout is 1 by 6. Then these raffle tickets. So that is a term related with basketball and stadium and persons who are allocated a particular seat. Okay, so you will read that. I'm not discussing all these examples, but in short, you can find several real life examples of uniform distributions also, just like you found several real life examples of normal distributions. Okay, so please visit these two sites here, because these are very, very important. Okay, here some more examples of normal distributions are given in the psychology side. For example, IQ is also follow human IQ, that also follows normal distribution. Newborn weight we have seen, height we have seen, shoe size we have seen, tact score, retirement age, blood pressure. So I think these are all the same thing. IQ is not mentioned anywhere, but IQ also follows normal distribution or bell curve. Okay, so that means that on this axis, if IQ is plotted, then the number of people having super high IQ are very less, and number of people who are having super low IQ, that is also very less. Majority of the people will have some in between values of IQ, maybe around 100 or 90 to something, 110 or something like that. I don't know what is the normal range, but majority of the people will have that usual range. So count will be maximum here will be around 90 to maybe 110. But 145 or 150 IQ, so very few people, genius people will have, and maybe here 65 IQ. So that also will be very few people, right? Okay. So that is also example of normal distribution. And this popcorn and this sand passing through the sieve, that should keep this whole concept of normal distribution permanently in your mind, right? Next time, in next lecture, we will do this binomial distribution, okay, and further discussion about other distribution. Thank you, and see you in the next lecture.